let's look at this very simple example.
Can there be a security for resending?
Do you mean to ask if data can get lost? No, MPI is going to use whatever mechanism the underlying network provides for it to do lossless data sending. So it is guaranteed, I think I have a slide on that. It is guaranteed that your data will get there. It is guaranteed that it will get there in the order you sent them. Okay. But whether the receiver is ready to receive or whether the receiver went through one receive call and got somebody else's data that fit that profile, and hence your data never got received, it will keep waiting. That can happen. But all the sends that you make will to a given recipient will get there in the order you made them.
How do you check the performance when there's so many factors involved?
So the only real way to check performance is look at wall clock time. Right? You've got a job to do and you start. When the job is done, you look at the wall clock time.
It can be different for...
It can be different, and as a matter of fact, that is one of the reasons that, especially in the context of parallel programming, scalability becomes an important metric. Where you say, what happens if I run it on 2 processors, 4 processors, 8 processors, 16 processors? What happens if I run it on a bigger data set? Okay, so that's kind of bringing back the notions of complexity. We will talk about complexity, but that will be in the context of a PRAM or something. But you'll see that there is a correspondence, so that if an algorithm has a lower big O complexity, then it's going to be fast on OpenMP. Given big enough problem size, it's going to be fast as an MPI as well. All right, so here is the main program. It includes mpi.h. Right? So basically you have to include mpi.h and later do MPICC to compile. Those are the 2 things. And when you do MPICC, it knows where to get mpi.h from. So -i is added in. You do MPI init. Okay, and MPI init takes arguments. We're not going to talk about that. It is checking for the size of its communicator, for the world communicator, and its rank within it. Okay, so it's akin to saying in OpenMP, my rank is equal to OMP get my thread num. Okay, here you have to make the function call and give the pointer to my rank, and it's going to get returned that value. Similarly, it's also getting the group size. How many? This is all being determined dynamically, right? The way MPI run was executed will determine how many elements there are. Rank is somehow it's going to get assigned. A unique rank will get assigned. Who is going to be 1, who is going to be 2 is indeterminate. And then I say do processing. After processing is done, MPI finish. And so do processing has a few local variables that the names are clear enough what they do. So I'm not going to go through them. When they are used, it will be clear. And this is really the main part of what each executable is doing. Okay, it says if my rank is not 0, right? So everybody whose rank is not 0, so we'll somehow say that 0 has become the master, everybody else is slave. So everybody else says destination is 0. Okay, everybody is going to send something to the 0th process, and then it sends a message. Message only says hello from my whoever is sending it. What is tag? We don't care as long as everybody is using the same tag, so we are setting it to 0. World is being communicated. We are sending string length of message plus 1 character array, and so that's what's being used. Okay. Now P0 says I've got so many different people who may be sending me something. So it says source equal to 1 to number of processors. Receive something from that source. This is not the only way to receive, but it is serializing. It says I'm going to read once first, then 2s, then 3s, which means if 3s came first, it better wait. It's going to have to wait. And then it is going to print what it got from the message. And if MPI receive didn't succeed, then it's going to say fail. All MPI methods return a success code. Okay, so if it returns you MPI success, which is 0, MPI success would be non-zero, I suppose. Then it succeeded, otherwise something went wrong.
So all these different computers open different ports on CPU.
All these computers open different ports. That's not even necessarily clear, right? Ports are very specific to TCP/IP. This may not even be running on TCP/IP. Exact details of it, I don't know, but it would be unnecessary to use different ports for different connections. Okay, everybody may be can be connecting on the same port, and you simply read, you select.
As the programmer, can I tune what would be the buffer sizes and all?
Yes. So those are some of the details that remain, and we'll take them up on Monday. I want to give you a second quiz on memory consistency, which is essentially the same thing, just a different sequence. Okay, so it's the same question, different detail, different thread sequences, and you've got to figure out which is the strictest consistency model. Any questions? We were talking about MPI, and here is a basic chunk of MPI code, which essentially tells you all there is to know at a high level. There are lots of details that we still want to talk about. But any questions before we move further from this? Okay. So there is a send. So in this case, if your rank is my rank is not equal to 0. Sorry, question.
So we say that there is this communicator that we have specified, and we use this global communicator MPI convert. So
not always. You can create new communicators.
Yeah, but my question is, if I have two programs, both use this MPI convert. So are there MPI converts different? Or
Yes.
They are different.
Yes. All the ones that were started with MPI run, okay, get their convert. And in fact, there was a question about why some different ports cannot be used. Actually, MPI does use large port numbers internally. It uses SSH only to get started, only to validate you, to authenticate you so that your process can begin on the remote machine. But then later on, the communication happens through, if it is a TCP IP machine, through sockets. And there is some discussion on MPI forums about whether users should be able to control the port that communication happens on. Currently, there is no such control. So it automatically determines, it tries sockets, ports, and if that port is being used by somebody else, it tries some other port. So it has some heuristics for which port it's going to use. There is some discussion about whether user should have a say in it. User can say, use range from 5000 to 5010 or something of that sort. So they do use sockets.
So, sir, while running this code, we specify the IP number of the computer that we.
When you start, yes.
So it means that on all computers I'm starting, I have to specify these IP numbers on all the computers.
Right. Or host names. Yeah. If you look at the starting program, right, the command, when we had an example of starting the hello world, it said mpi run minus mp4 said that run it 4 times. But you can give it a list of machines. You can also give it a host file. Okay, so you can say dash host file, give it a file name. You can list machines as well as how many times you want to run it on each machine in a file also. But yes, it's going to do a lookup on the host name in order to get to it.
But is this method scalable in case like when there are thousands of hosts and every minute there is some host which is failing, every minute there is new host which is spawning up? Wouldn't a master server type of architecture be
Yes.
fault tolerant inbuilt in this thing?
No. So MPI doesn't have any inbuilt fault tolerance, and it is not for that kind of environment where lots of nodes are going up and down, which means you have to put some layer on top of MPI to allow for that to happen. And as a matter of fact, in any very large, for example, top 50 or top 100 even HPC machines, would have something built on top of MPI or their own from scratch communication layer. Because they know that once the number of nodes start to go very high, then you do need to worry about nodes going down and coming up. But MPI is blind to that.
And if one of the hosts goes down, what will happen? Everything will stall. Or
Eventually, everything will stop, right? So things can go on because you're sending somebody to that host, but at some point there is internal handshake that people are waiting for, and definitely if you do barrier or things of that sort, definitely it's going to hang. Yeah. Okay, so there is Mpi Send, Mpi Receive, and in this case the protocol is that, in fact in this example, you go through a loop of receives, right? If you either you're sending to one master, so to speak, or you're receiving from all the slaves. And so you say, for every slave, receive from that slave. Okay, which means that guy sent and your receive is going to get matched, and then you're going to potentially proceed. Okay, so there is a level of synchronization associated with it, and we have to worry about whether we can control that level of synchronization. Question.
I was asking, does it matter if the send comes before the receive? Like if the receive call, let's say thread 1 sends the message, but the receive function hasn't been called for thread 1, then is that a problem?
No. That would require pretty much a lockstep execution on both sides, right? That is a little too stringent. Just the fact that I cannot proceed from this send until somebody receives it is enough of a performance problem, right? Synchronization wise. And that's why that's the next kind of things we will be looking at. Do we need to have full, complete synchronization at send and receive? And as a matter of fact, even the vanilla, the default send and receive does not provide for that complete synchronization, or for that matter, wait for the complete synchronization. What it is though is blocking. Okay, so we've got to look at various aspects. If you were to do it, what would you do? I want to send. I want the data sent to be received somewhere, but I don't necessarily want to have to wait for it.
if I'm sure that my data is copied in other buffer, then I can
In whose buffer?
send it in the one
So for every send, you will spawn a thread.
all senders.
That could be lots of threads. If you're doing lots of communication, then potentially there are lots of
There's
threads.
one thread which is waiting, which is doing all the communication.
However, there are lots of threads that are waiting. You do a send, you do compute, you do another send, you do compute, you do another send. So one guy keeps computing, but it can keep generating these sends. And so every time it generates a send, another thread starts.
What I was saying was there are two threads. This is responsible for all the communication, not for all the computation. So it computes and gives it to this thread and moves on. And this thread manages what has.
How does it give to that thread?
The thread is on the same machine.
So on every machine there are two threads. One
Each other.
takes care of the data, something like the data and control channel in the network.
However, you still need to worry about synchronization between these two threads now.
Which is local.
Which,
Communication.
yes. Right? So for one is that the communication thread doesn't have one communication thread that it is talking to at another remote site. There are lots of them. And so that problem simply got postponed.
That particular thread can take care of all the buffers that need to be managed.
Right. So there's some buffer-based management that is required. Right? So that you can go on and this buffered data will get sent. What about on the receive side? You keep receiving something into a buffer, so some receiver thread or something keeps receiving it into the buffer, and at some point you say, I'm going to take it. What are the things that can go wrong with it? Buffer overflow? Well, underflow is not a problem in the sense that you are the original reader. So if you might have outsourced your reading and said, tell me when you're done, I'll come back later and actually read it. Or you just have to wait because it's not there in the buffer.
Yeah, that is.
So it's not underflow. Right? It was your responsibility to read it. So if you couldn't find somebody else to buffer it for you, or maybe it's not there, then you wait and read it, which was the original thing anyway. So there's a buffer overflow issue, which means you may want to control what size the buffer is. Are there other ways in which?
Two threads are sending. So I want to differentiate between two threads. So first, I'm expecting that thread 1 would send first and then 2 would send. So my receive call is first for thread 1 and thread 2, but they acknowledge in while it's sending. I need to differentiate that. This is from thread 1.
So somehow somebody needs to be able to receive from multiple, right, places. So that's one thing. And that somebody, maybe that communication thread, in fact, MPI will have a communication thread that you were suggesting. So you won't have to spawn a thread, but MPI will internally have a communication thread to which you will be talking. But you do need to understand that there is enough buffer with that communication thread, or you provide a buffer every time you send, or you say, I'm not going to touch this buffer until you have sent it. Okay, so there are lots of these different ways in which you might control this level of synchrony. One, at the highest level of synchrony, you say, I am going to proceed if that receive has received it. Okay, it's not just the matter of communication, but a complete synchronization. Because now that I have come out of my send, I know a receive has happened, so I can make assumptions about what code has executed on the other side. Okay. The next may be that I can continue if that guy has started receiving. These two are different. That guy may take a long time to receive, but once it has started receiving means it has allocated, if it has figured out there is so much amount of information coming, it has allocated the buffer space for that much communication, and it's going to receive it, guaranteed, unless something crashes, which we are not accounting for.
All these are semantics of this MPI, or we need to do that?
No, these are semantics inside MPI. You don't need to do that. So those are the different variants that it provides.
What happens if I'm sending and I want to? So these machines can be of different types, right? One may have high, like large memory, another may have small memory. I am sending some data, and the other memory, other machine which is the recipient doesn't even have that much memory available. Is that
So in this case, where you want to guarantee that receiving has started, there is underlying assumption that it starts only when it can finish. Right? Meaning it has enough buffer, it has figured out how much data you're sending, because that typically goes in the header. And it's allocated that much buffer, it found that much buffer somewhere, and it's going to receive it. There are other situations where you say, here is this piece of information, send it. Okay, and sometime later, come back and tell me that it was received. In that case, it may never get received, right? Because that other machine just couldn't get the buffer that it needed for.
but something of the sort of streaming, like, because for example, I need to send 1 GB of data to some other machine, and the other machine doesn't have 1 GB of buffer available. But because 1 GB data transfer itself takes some time, I'm sending, the other machine starts reading, and instead of allocating the whole space, it starts reading and starts processing the data, discards whatever is not needed, something of that sort.
So it is at the granularity of the send, okay? Meaning that you said, I'm going to send you 1 gigabytes, right?
Packet will be 1 GB.
So, no.
I mean, the MPI.
Right, so MPI is going to tell the other machine that you are going to receive 1 gigabytes. You need a buffer of 1 gigabytes. Okay? If that machine is not able to get 1 gigabytes, it's not going to be able to receive it, right? It's not even going to start. That's the end of story. Alternatively, it can be done on an opportunistic basis, where you don't allocate buffers. You say, you've got some buffer. I'm going to send you 1 gigabyte. You start reading, okay? And when you run out of buffer, you either wait for that buffer to get emptied and read by the application, or you stop. Okay, so all those are possibilities. Okay, so what you see here are those possibilities. Okay, there is this. So one way to differentiate between, or one axis along which you might differentiate them, is that either the function calls, send or receive, are blocking, or they're non-blocking. Blocking means something has to happen in terms of safety of this message being received before you will return, before that call will return. Okay. Non-blocking is, it will return right away, so to speak. Right away means that the underlying system will figure out, you want to send this, you want to send so many bytes, it's going to copy all those things, the information that you were saying, send so many bytes of, not bytes, so many ints from this memory location to that destination. It's going to copy those pieces of information and return. Right? So it is as if there is no waiting, because you're not waiting for some condition to happen. There's some local variables, the parameters to the send are being copied locally, and then the process of sending will begin in the background. Okay, so that's one axis. The other axis has to do with the buffering. All right, MPI by default has buffers, meaning that the second thread you're talking about, the communication thread, has a buffer. So when you make a function call, that buffer is going to copy from your buffer. Remember, when you say send something, you're providing a pointer. You're providing an array full of data. And when you provide this array full of data, that array full of data will ultimately get copied into an array full of data on the recipient side. That's what you goal. That's what you want. When the receiver calls its receive function with a pointer, your data is going to appear there. But it may go through a sequence of buffers along the way. Okay, and one of those will be MPI's buffer, and if MPI has space, it's going to keep in that buffer. If it doesn't have space, it's not going to return your blocking call. Okay, so it is blocking in the sense that if MPI is able to copy from your memory location to its buffer area, you're done. It's safe that your data is going to get sent from here. You can proceed and reuse that array to write more data or whatever you may wish. Right? When you do that, there is also a need to know that this information has been received. Right? Because just because the data was copied to your buffer doesn't mean it's going to eventually get there. It may run out of buffer somewhere else. And not just whether it reaches there at some point, you may also want to know whether it has reached there now. Okay, so you may want to say hide some latency by saying, I'm going to send this piece of data, then I'm going to do all this computation, and then I'm going to wait because I need to make sure that that data got there before I can proceed beyond this point. So at that point, you need some way to check. Okay, there are two possibilities. One is that this communication thread somehow tells you that yes, you had sent something, it has gone through, or you query. You query saying, I had sent this, did it go through? If it didn't go through, you either now wait, or you go do something else and come back and check, did it go through? Okay. We'll look at how you do those tests, but the modes that are provided is the standard, send and receive. It's until the message has been received. There is something called standard mode, which is implementation's choice. It's like the chef's choice. Okay, whatever is going to work the best at that moment, the implementation is going to choose for you dynamically. It can change from call to call.
It's standard. Then why it's called standard?
Standard means you don't have to specify anything. It's the default. The default is that it's going to figure out what it can do. Otherwise, there is a buffered mode where you provide the buffer. There is always some buffer. Even when it is not buffered mode, MPI is going to copy it into some buffer of itself. But you don't know how big that buffer is. So you may say, I'm going to send gigabytes of data. So here is 1 gigabyte array. You copy into this. And then I'm going to do non-blocking. I'm going to say send, and I'm going to want to go do something else. You return immediately, make a copy into this 1 gigabyte array that I'm giving you, and let me go do something else.
So is there a way to avoid this copying part? If I have allocated the data already in my program for my purposes, and then I just give that allocation directly, use this allocation, I'm not going to use this part of memory again. So is this possible? Because this copying of data can take time.
So again, MPI is a standard and an implementation. The standard doesn't say anything about it. But an implementation may choose to optimize, and I don't know whether OpenMPI does or not. if you in the buffer provide the same address that you have provided in the send call. Right? So buffer says, here is a buffer when you can make that copy. If that buffer address is the same as the address call that you provided in the send, then you know that there is no copy needed. You want to copy to the same place where it is. Right? So it might do that optimization, but the standard doesn't say anything about it.
You should be doing some bookkeeping in the buffer space.
For that, it's not going to get rid of its internal variables completely. Right? So it need not, when you say I have got this much buffer, you expect it to use all of it for your business. There is a synchronous mode, which, as the name suggests, it says something about the receive on the other end. Okay, the receive is completed, and only then will it return. There is also something called a ready mode, which is the receive has started. Receive knows how much data is coming. It is going to complete. So if I don't need to know that it actually has received all the data, then I can proceed, because I know that because that receive has started, everything that was before that receive has been done by now. Okay, if that's all the level of synchronization I needed, I can simply say, if the receive is ready to receive, then I can go and do something else now. Okay.
And if it's ready to receive, then MPI guarantees that it will receive it.
If it is ready to receive and it is buffered, right? Only then. MPI is not going to guarantee that it's going to have enough buffer to receive it. It only says that receive function has been called. MPI has seen the receive call, it has looked at the parameters of the receive call. That's it. Okay. It means your send has been matched with that receive. That receive call has been made. Okay. The function names say what they are. Send is the blocking send we saw earlier. There is which is the standard send. There is a buffered send for bsend, the same name. And again, I'm only giving you the C version. There is a C++ version where it will be MPI : bsend. Send is for synchronous send, rsend is for ready send, and receive is only one. Yeah, because all of this control is happening on the sender side. Receive can also be blocking and non-blocking. But the buffering and synchronous is not business of receiver. Okay? Blocking and non-blocking. We'll get into one more level of detail. One mode in terms of the buffering. Buffering, synchrony, and ready. Receive, you can only say, receive now, and when the data is here, return to me. Or, I'm ready to receive. I can go do something else, but I have reached this point, and I'm giving you this buffer where to give me the result. The messages are guaranteed to not be lost. Again, this depends on servers not crashing and all that. They are guaranteed to be in order, meaning that if you send a stream of messages to a given recipient, they'll be received in order. Okay? Because there is no global clock. There's no global synchronization that I sent and some other sender sent, then our sends are ordered in any way. Okay. There is also progress that if I call send, you call receive, then the data will get through. Okay, as long as you're providing enough buffer to read it into. Fairness is not guaranteed. What that means is that if two, so you can match sends and receives, right? You can say send to this processor ID 3 or process ID 3, and somebody else might, in the same group, same communicator, may also be sending to process ID 3, and 3 does a receive. This is kind of like a race condition in the shared memory context. Okay? 2 senders sending to 1 recipient with exactly the same tag. Right? And the recipient says receive from anybody. If the recipient says receive from sender number 1, then 1 is going to get matched, no problem. But if the recipient says receive from any sender, then one of these senders' calls will get matched, and the other will have to wait for another match. So starvation is possible in the sense that I do a send, and this other processor does 50 sends, and that fellow does 50 receives, and all the 50 receives came from that guy. Okay, even though I did it first. It's not guaranteed because there is no ordering between us. Okay.
So why is that at least one of the flow progress in the progress?
It has to do with ensuring that there is enough buffer on the 2 sides.
Okay, so my even at least one then is not enough buffer on both sides.
At least one meaning that the sender says, I'm giving you this much data, right? And there may be all these different modes. And one mode says you do standard, do whatever you can. And so on the other side, there is not enough buffer to receive everything. Okay? If I keep what's going to happen? That the user is going to give you an array, right? So the recipient doesn't have enough buffer, but the user has given you that 1 gigabyte buffer. Okay? So you're going to keep taking more and more of the data and putting it from your buffer into the recipient's buffer, right? And so at some point, either the sender will have sent all data and the recipient either ran out of buffer, right? Or the recipient has, so in this case, the sender will end. When will the recipient end?
So it says for a matching pair, right? So if the sender fails, the matching won't be done at all. Then the receiver will just continue with.
No. I'm trying to think why I wrote this. It's matching pair means there is a matching pair. The matching pair has been found. Okay.
That means sender has been succeed. Okay.
No. So no. Now I know. Now I remember what I meant. When you send, and recipient says, I've got the same tag, but receive from any. Right? So your send would match with that receive, but hasn't necessarily been matched with it. Right? Your send also matches, that other send also matches with the same receive. Right? Which means you two match with each other. So either you will be able to send or he will be able to receive. He may be able to receive from somebody else, in which case your send didn't go through. But one of these two will go through. Okay? At least one. Sorry? We just talked about the case where receive might not go through. Right? And sends are also broadcasts. Although there are more conditions on broadcast, we'll talk about that also. Deadlocks can happen because there is no direct or no underlying methodology to say that I am going to be before you. You do a send, that guy does a receive, and then when the two things match, the data transfer takes place. Okay, if you send to this fellow, and that guy is receiving from that fellow, and that fellow is sending to you, and you're all blocking, then you're all waiting for each other. Okay? So if the user, it's up to the user to make sure that every thread or process can proceed, and which means that user needs to make sure that there are no deadlocks. Okay, here is the asynchronous version, and again, all those variants will apply. So you can say Mpi I send, Mpi IB send, Mpi IS send, Mpi IR send for the buffered, synchronous, and ready versions. Okay, so those all go with I, and we'll look at. In fact, it would probably make more sense to look at the function call. So in interactive send, you send a buffer, you provide a buffer just like before. You give a count, you say what type of data you're sending, you say here is the destination, here is the tag, here is the communicator, and then there is a MPI request type variable. Right? You allocate a variable, send its address, and that becomes an identifier, a handle for this specific request that you have made. So you can do lots of sends if you want to pipeline sends. Each one will return to you one request. And it is this request that you use later on to test whether this request has succeeded or not. Okay? And similarly on the receive side, if you want to do non-blocking receive, then you must get this request back. If you want to check whether your receive is done, you make a function call, which we'll talk about shortly, on this request variable. Okay, and the function calls you can make are wait, where you say, now I'm done sending. Now let me see whether my receiver, my call that I had made is done or not. If it is done, good. If it is not done, then wait for it to get done. Okay, so Mpi Wait is blocking variant of send. So instead of you blocking at send, you did some other things, and now you're blocked until your send over there got completed. Alternatively, you can simply test. So test is the non-blocking version, where it will simply return saying, no, it's not done yet. Or, yes, it has been done now.
Like, if the test does not pass, then you can do some more stuff and then it.
Yes. So it's polling versus sleeping on it.
But could this not have been similar to having a lock and if you wait on that lock? I mean, binary is another semantic.
Somehow you have to associate that lock with that send.
Right, and that Mpi couldn't do that. Locks are more fundamental than Mpi.
How is it any different?
Lock does not give you these many options.
There's more, of course. What can go wrong if I give you these two, wait and test?
What if the request never comes to it?
That means there's probably a deadlock, right? You may be starved, but eventually everybody else will get through, and then if you're not deadlocked, then your request will succeed. But I just said that you can be pipelining these. So how can you wait on one of them?
MPI test is available, then what's the need of MPI Wait?
So test is poll based, right? You have to keep testing. So if you have nothing else if you have something else to do, then test makes sense. If nothing else to do, then it's in a loop, right? While MPI test is equal to 0, semicolon.
Wait also is in some sense infinite loop.
But you are not using up resources, right? Your process has been put in a sleep mode, and it will be scheduled only when the system has determined that you can be woken up. Right? So you are not using up any resource at that point. You are using memory and all that, but you're not being scheduled to run any of your instructions. And so it's much more efficient, especially if you're doing lots of them. And especially if you have lots of processes running on your machine, which may be doing something else, even if you don't have anything to do.
MPI test is on spin log.
MPI test is a spin log. So in MPI Wait, especially, it turns out you can do with MPI test also. There is a variant where you can wait for more than one. I'm not going to talk about those variants. There is MPI request get status and MPI request. MPI request free is not a variant. You have to do it when you've created a variable called request. That request has been filled with information, and system is monitoring something about that request. So once you're done, you must free that request. Otherwise, it keeps taking MPI memory resources inside MPI, and so you'll be able to get fewer more requests done. You can also separately get the status of the request, which is slight variant on MPI test, but the function that is a little more useful is MPI Wait Any, where you say how many things you're waiting for, and here is an array of requests. So if you want to wait for everything, you say MPI Wait All. But if you want to wait for some subset, then you create a request array and get only waiting done for those. Wait all means every request that you've made is done. Okay. There's also wait sum, which is very similar to wait any. In wait any, you give it an array and it will return if any of those requests have been satisfied. In wait sum, you get to say some of them, right? Some number of them have been satisfied. Okay, on the recipient side, you also get some information about the message that you are receiving. So you can peek into a message that you haven't fully received yet. Okay, and so there is an MPI probe to peek into the message, and it's got the same information that you would have about a message, and it will tell you something about what the size of the message is, the message that's being received, and all that. You can cancel a request also, just in case you don't want it anymore. You have made a request. Cancel doesn't necessarily mean it won't happen, because it may be too far down, but it just hasn't been completed, so a request done flag hasn't been set yet. But if you see that it's not done, you can try to cancel it. Okay? It's more a request than an assurance that it will get cancelled. But then you can test whether it got cancelled or not, whether it still went through after you cancelled, or your cancelled took effect. Okay, I think we probably need to stop at this point, take a small break, and have a little bit more on Mpi Send and Receive before looking at the other aspects of it.